Good afternoon, everyone. How are you all? So, in the previous class, hello JNV Rowing. In the previous class, I have given you a homework question. So, have you done that question? So, we will start with that homework question first. Was that the question? If I read the question, first of all, just let me know, am I audible properly or my screen is visible? Okay. Option C. Very good, JNV Rowing. You have attempted the question. That's really good. I appreciate. Now, if I go through with the question very quickly, a galvanometer having 30 divisions has current sensitivity of 20 microampere per division. That means if you can see there is a galvanometer, let's suppose this is the galvanometer and in total it has 30 divisions like this. 1, 2, 3, 4 and like this there are total 30 divisions. So out of these 30 divisions, it has a current sensitivity of 20 microampere per division. That means for one, the current sensitivity is given as 20 microampere per division. So if you can decode the unit here, microampere per division, that means 20 microampere current is needed for the deflection of one division. Are you getting my point? 20 microampere current is needed for the deflection of one division. Now, how many divisions are there? 30 divisions. So find the maximum current. So for maximum current, you can see that one division is deflected by 20 microampere. Then for 30 divisions, how much current is required? You will say 20 into 30 microampere. So that will be 600 microampere. That's very easy and very good question to understand the concept. Clear? And this current that I am talking about, the maximum current in the galvanometer that we can read is generally known as full scale deflection current. So try to remember one word here, full scale deflection current. What is full scale deflection current? The current required to deflect the needle completely in the galvanometer is called full scale deflection current that we will require in the later section on the next section. So on this note, I am just moving to the next slide. Now there is a very important topic, conversion of galvanometer. This galvanometer you have seen, we can detect the current using this galvanometer. And generally, the current which we can measure using galvanometer is of the order of few microampere or somewhat some milliampere only, not more than that. That means very small amount of current can be measured using galvanometer. Now, how we can convert it into some other form like in the form of ammeter and voltmeter? These are the two big questions. So one thing that I will answer here or you should remember all the time, ammeter is a device used to measure current, that is used to measure current. For current, I have written as I. One thing. The device which is used to measure current is always connected in series with the circuit. So next point you should remember, always connected in series with the circuit. So two things you should know. Now, consider the situation I am telling. Let's suppose this is the resistor. This resistor is a part of a circuit. This resistor is a part of a circuit and has some resistance R. Try to be interactive. try to say yes, no, whatever the time required, and you want to measure a current in it. Let's suppose, now consider the situation. Whenever you see a meter, there is a limit up to which it can measure. It can measure. Are you getting my point? You have some devices, for example, you have like the voltage regulator, the voltage stabilizer you have seen in your houses. It has some readings. The speedometer of your bike, of your scooty, of your anything has some limit. It has some limit 80, 90, 100 kilometer per hour, 200 kilometer per hour, like that. So every meter has a limitation. In the same way, a meter also has a limitation. So what I'm saying, that range of the emitter that you want to convert. So minimum value that it can measure is 0 and the maximum value is I. Clear? So what is the maximum value it can measure is I. So I am designing the emitter in such a way to use it for the maximum current. Let's suppose the resistance has the maximum current I, and I have attached a galvanometer in series with it. I have attached a galvanometer in series with it, like this. This is a galvanometer G. Now, to convert it in the form of a emitter, what I did, I have connected a very small resistance. Try to listen each and every word very carefully. Very small resistance in parallel to the galvanometer. And this very small resistance is known as shunt and denoted by S. So this combination of galvanometer with a shunt is known as ammeter. Try to listen each and every word. What I'm saying, combination of galvanometer with shunt in parallel is called ammeter. So if someone asks you how will you convert galvanometer into ammeter, your answer should be very much clear that we will connect a shunt in parallel to the galvanometer. Now, shunt is what? A resistance which has very small magnitude. Clear? Now listen to one more thing here. If I write something here, you can see. Can you see one thing? The current I is entering, and at this point, look at this point. Current can be divided in two parts. Current can be divided in two parts. Now, the current which is entering is maximum. This is the maximum current. You can see that this is the maximum current. So the needle of the galvanometer should deflect to the maximum value. What I'm saying, I'm repeating my words. If the current which is entering the circuit or which is in the circuit is maximum, that my meter can measure, then the needle should move to the maximum point, and this maximum current, what we named it as full scale deflection current. On the previous slide, we have given a name maximum current as full scale deflection current. And this is denoted by IG. I will write it anywhere else in the screen. What is IG? Full scale deflection current. So the remaining current will be what? Can anyone answer? This simple question, what will be the remaining current in the circuit? If I is entering, IG is going in the galvanometer, what will be the remaining current? Can you tell me? You can just say yes or no. If you can't write, you can say yes or no. Otherwise, it's very simple to write down. Okay, my voice is not good. Okay, just confirm me. Is it good now? Am I audible properly now? Okay, Yani, I will try to figure out the things. Okay, I'm checking my internet connection as well. It was good. Yes, confirm me. Anyone else who is facing the same problem of the audio? Anyone else? Manjo, Yeli, anyone else is facing the same problem? JNV rowing, is my voice clear? Okay, okay. Now we are moving further. What I was saying, I was asking one thing. I current is entering from this point. You can see that, and IG is going in this direction. Then how much current will move in this direction? How much current will move in this direction? You can apply KCL, and this current you will find as I minus IG. I hope you remember KCL, Kirchhoff current law, or the junction law. Hook is also here. I minus IG is the current. Now, can you see that shunt and this galvanometer is or are in parallel? Where G is what? G is the resistance of the galvanometer. If you remember from the previous class, G is the resistance of the galvanometer, and these two resistors are in parallel. So the condition of parallel combination is what? Potential remains same. So what I can say, shunt S and galvanometer G are in parallel. So the potential will remain same, and potential is what? You can say potential across this is V equals to I into R. So current in this is IG. Resistance of this branch is G is equals to current in the shunt branch is I minus IG into resistance is what? S. So this is the golden equation whenever they ask you to convert a galvanometer into ammeter. This is the equation that you must use. Now, what is the meaning of each and every term? If I say, if you ask me what is IG, I have told you IG is the full scale deflection current. What is G? Resistance of galvanometer. Can you read it out? Resistance of galvanometer. What is the another term? Is I, maximum rating of ammeter. Maximum rating of ammeter means the maximum value that your ammeter can measure. And what is S? S is the shunt. S is the shunt. I hope every term is clear here. Now, one more thing, which is again very important about the galvanometer, about the ammeter, I will say. If you can see the very famous question of NEET exam, I will say, what is the effective resistance of the ammeter? The question is, what is the effective resistance of the ammeter, or I will say, what is the resistance of ammeter? What is the resistance of ammeter? If you look closely, ammeter is a combination of, ammeter is a combination of, you can see here, shunt and galvanometer. Is it clear? Shunt and galvanometer. It is the combination. Now, you can say resistance of ammeter is a combination. So in parallel combination, how you write the effective resistance? You will say product over sum. That means S into G over S plus G. Product over sum. 1 by R1 plus 1 by R2. That's the way you calculate the effective resistance in parallel combination. Now again, if I say effective resistance of ammeter will be in this relation, S is very small. You know that S is very small resistance, so you can neglect this S to be 0. Why 0? Because it is very small. So what it will become? S into G divided by G, out of which G can be cancelled. So resistance of ammeter is approximately equal to the shunt. This is again very interesting fact that resistance of ammeter is nearly equal to the shunt, and shunt resistance is very small. So the conclusion is resistance of ammeter is negligible or resistance of ammeter is very small. Is this point clear? So what is the conclusion? Resistance of ammeter is very small. The conclusion is clear. You can write it down on your notebook or whatever you have. Next punchline: if resistance of ammeter is very small, then the next punchline is for ideal ammeter, resistance is 0. So try to figure out these things, how things are happening. For ideal ammeter, effective resistance is what? 0. Clear? I think first topic is clear. Conversion of galvanometer into ammeter. Say yes if it is. And then we will move further. Try to note down everything on your screen, or you can take the screenshot as well. Now I am moving further. Now another point is what is how we can convert voltmeter. Now listen. Again, two punchlines. Very good, JNV rowing. Very good. Try to be responsive the same way. One thing, voltmeter measures what? Measures voltage. One thing is clear. Now, any voltage measuring device is always connected in parallel. So you can again write always connected in parallel. I hope these two things are clear. Measures voltage and always connected in parallel. Now listen to me again. One thing, you are converting galvanometer into voltmeter. So what is the first thing? That is the range. So what will be the range? I am saying, let's suppose you want to convert it in the range of 0 to V. V can be any value like 10 volt, like 0 to 20 volt. So V can be any numerical value. Okay. Now, let's suppose you have some resistor, some part of a circuit like this. This is the part of the circuit R. And in this resistor, let's suppose this is the resistance R. In this resistor, you want to measure the potential difference. You want to measure the potential across this resistor. So first thing that you can do is you will connect a galvanometer parallel to it. So I am connecting a galvanometer parallel to it because voltage measuring devices are connected in parallel. So I am connecting a galvanometer parallel to it. Now to convert it into a voltmeter, what I will do, I will connect a very high resistance in series with it. Very high resistance is termed as R. This is G is our galvanometer. R is very high resistance. So I am writing it here very high. Shunt was very small. This resistance was very high. And this combination is known as voltmeter. Clear? Now, for the measurement purpose, let's suppose the potential across this resistor is V, which is the maximum potential, and suppose current entering from here is I. So for maximum potential, current to reach here is full scale deflection current, that is IG. Again, you can see that what you can see that these two branches named as 1 and 2 are parallel to each other. And if these two branches are parallel to each other, the potential across them will be equal. So you can write it as V potential across branch 1 should be equals to potential across branch 2. And branch 2 has some current Ig. How you can write the potential? Potential is I into R. What is the resistance of this branch? This branch has two resistances. One is G, another is R. So total resistance is G plus. So this is the total resistance of the, or this is the golden equation for the conversion into voltmeter. Can you remember these equations or can you remember this diagram? My recommendation is to remember the diagram. Just remember the diagram of both the situation, not the equation. Like in the previous slide, you can remember this diagram. So you can easily form the equation. How you can form the equation? The potential of two branches will be same. Galvanometer will have full scale deflection current. So Ig into G is equals to I minus Ig into S. You can directly write the equation. Similarly, here you can directly write the equation if you can remember the diagram. I hope till now everything is clear. Now, one more thing. What is the thing? Resistance of voltmeter. Out of this circuit, which is known as voltmeter, the combination of galvanometer and the series resistor is known as voltmeter. So this combination is known as voltmeter. So resistance of voltmeter R resistance V for voltmeter is equals to series combination. And in series combination, effective resistance is R1 plus R2, or you can say that G plus R. This is the effective resistance. Out of which, do you remember one thing? R is a very high resistance. So the resistance of voltmeter is very high. So you can make a punchline again. Resistance of voltmeter is very high. Then what will be the resistance of ideal voltmeter? Can anyone answer here? What will be the resistance of ideal voltmeter? Resistance of ideal voltmeter will be, if normal voltmeter has very high resistance, then ideal voltmeter will have infinite resistance. So try to remember one more punchline that I have mentioned here. Will have infinite resistance. These question of ideal voltmeter and ideal ammeter are very common. I hope this is clear. Now, moving further. There is a practice question on your screen. I will give you some 30 seconds and just try to attempt and give me the answer whether A, B, C, or D. You have four options. And you can see that they are asking for close to, that means some approximate answer they are asking. They are not asking the exact answer. This question was asked in 2019 JEE mains examination, and it will give you an idea that what kind of questions usually come to our exam. Say at least present, sir, so that uh, I can know that who are the persons present right now in the class. I can see only JNV rowing is present. Fuku is also present, I can see. Manjo is present, very good. Some six persons are present, na? Very good. Yani, okay. Are you trying to solve the question? 20 volt. JNV rowing is saying 20. Yeli is also present. Very good, Yeli. Very good. 20 volt is answered by JNV rowing. Let's check the answer. So they are saying there is a moving coil galvanometer has some resistance of 50 ohm. So first of all, you should name what is given. So resistance of galvanometer is denoted by G. Now listen to me very carefully. If you have no idea, you can note down everything. Resistance of galvanometer is given as 50 ohm. Very good. And it indicates full deflection at 4 milliampere current. Now, full deflection means full scale deflection current, that is denoted by what? Ig. Full scale deflection current, that is 4 milliampere. You can write it as 4 into 10 raised to the power minus 3 ampere. Clear? Now, next thing is a voltmeter is made using this galvanometer and a 5 kilo ohm resistance. Now, they are converting it into a voltmeter and has attached a resistance of 5 kilo ohm. So the external resistance given is 5 kilo ohm, that means 5000 ohm. Clear? The maximum voltage. So maximum voltage we have denoted by V, they are asking. Now, if you can remember, the golden equation formed for the conversion of voltmeter was somewhat like V is equals to, I can remember the uh, one branch has potential V and another branch has potential Ig into G plus R. Was that the case? V, they are asking, Ig is given as 4 into 10 raised to the power minus 3. G plus R, if you can see, G is 50, R is 5000. If you add these terms, it will become 5050. Clear? Is equals to V. Now, if you can simplify the things, this 10 raised to the power minus 3 can bring decimal here. Is it clear? Uh, uh, can bring decimal at this point. 10 raised power minus 3. So this is 5 fours are 20 point something, or you can say V is approximately 20 volt. Very good, JNV rowing. Very good. So which is option number D? Very good. So we have one more question. I will give you again some 30 seconds to solve this question. And that's really good that you are solving the question. Try it again. Okay, till then, just answer me one thing. Which chapter is going on in your classes? Right now, which chapter is going on in your classes? Just answer this question and continue solving the given question. EMI. Okay, EMI. Very good. That means you are ahead of this one. So you should answer ray optics. Very good, Isli. Who is saying EMI? That means you have completed this chapter. Okay, then we should gain some pace. Then support. then give me the support, needed support now, so that we can move faster. Okay. From the next class, we will try to be more faster, and you should answer then. That's my concern was like you were like on current electricity. Someone answered in the previous class that you were in the current electricity chapter. That's why I was running a bit slow. So now we can do it very quickly. The question says the current sensitivity of a moving coil galvanometer increases by 20%. So do you remember the formula of current sensitivity and the voltage sensitivity? Calculate by what factor does the voltage sensitivity change. So you should remember the relation between voltage sensitivity and current sensitivity. So what is voltage sensitivity? If I can recall the things, voltage sensitivity is what? Current sensitivity divided by resistance of the galvanometer, which is denoted by G. So Vs is equals to Is over G. Now they are asking about the change. So whenever they are asking the change, you can take the ratios. The basic practice is take the ratios. So I will say voltage sensitivity in the first case, voltage sensitivity in the second case is equals to, it is directly proportional to the current sensitivity, that is Is1 over Is2 into G2 over G1. If you face any problem in this step, you can ask me. Otherwise, I am moving further. Now, what they are saying, current sensitivity increases by 20%. That means initially, if it was 100, then finally it has become 120, because increased by 20. Is it clear? Now, they are saying that resistance is increased by a factor 2. That means, let's suppose initial resistance is 1, G1 is 1, then final resistance is increased by 2, that means 2. Clear? You can solve this. 0 and 0 can be cancelled. So what you get, voltage sensitivity in first case divided by voltage sensitivity in second case is equals to, can you solve it out? 2, 6 are 12. So 10 by 6, that is 5 by 3. This is the ratio of voltage sensitivities. Now, what you can see, voltage sensitivity decreases by 2. Can you see that? Or you can say percentage change in voltage sensitivity is what? You can see that change is of 2. It is decreased by 2. Original value is 5 into 100. What it will be? 40%. This is the answer. So what is the correct answer? Option A is the correct answer. Now you can ask me if you face any problem in any of these steps. Like if you face problem from this step, say star. And if you face problem in this step, say, what is this? Say hashtag. Or if you have no problem, 3 by 5, hashtag. Okay. Okay. So I am starting with hashtag. What is this? This is voltage sensitivity. For first term, you can see, you can learn this thing from right now. Voltage sensitivity is directly proportional to the current sensitivity. That means if I take first case, then I should take the first case of current sensitivity. Both will be on the numerator side, that Vs1. So here is Is1. Here Vs2. So it should be Vs2. Now voltage sensitivity is reciprocal to G. That means where in the numerator I write Vs1, I will write G2. That means it is inversely proportional. Like some quantity you can say, like force is inversely proportional to R. Suppose that. Then what you will write, F1 over F2 is equals to R2 over R1, because it is inversely proportional. That's why I have written it. I hope the doubt is clear. If some quantity is inversely proportional, you should make it inverse 1, like that. Now 5 by 3, if I talk about, the ratio of these two quantities is coming to be 5 by 3. If the ratio is 5 by 3, you can see this is original. VS1 was original case, VS2 was final case. So voltage sensitivity original was 5 and new voltage sensitivity was 3. That means how much it is decreased? It is decreased by 2. And what was the origin? How you calculate the percentage change? The change in the value divided by original value into 100. So what is the change in the value? 2. What is the original value? 5 multiplied by 100. What if this ratio comes out to be, let's suppose 3 by 5? So you can say it is increased by 2. What is the original value? 3 into 100. So that's how you calculate the ratios. You calculate the percentages. In the students who are preparing for these exams must definitely know these tricks. So moving further for today's topic, Earth's magnetism. Okay, once more, coming back to the once more. I hope you are asking about this point now. I'm repeating my word. Let's suppose if I talk about just percentage thing, let's suppose you got 30 marks out of 50. How many marks you got? 30 out of 50. So how will you calculate the percentage? You will get marks you got 30 divided by original marks into 100. That's how you calculate percentage. In the same way, when some things are changing, like you have seen in change of resistance cases or some change in length cases, like initial length, I will say, let's suppose 100 centimeter. Initial length. Try to focus. I'm not writing much. Initial length is 100 centimeter and it is increased to 120 centimeter. So what is the percentage change? What is the percentage change? Do you know that? What is the percentage change? You will say, yes, sir. What is the change actually? The change is 20 divided by original value is 100 multiplied by 100. So what is the change? 20%. Now coming back to our ratio, our thing, this is the ratio 5 by 3. This VS1 indicates initial, 1 is taken as initial, 2 is taken as final. This is the final value. So what is the change? You can say change is of 2. The change is by 2, decreased by 2. What is the original value? That is initial value is 5 multiplied by 100. So that's how you calculate the percentage. Now tell me if this ratio comes out to be something 4 by 5. If this ratio comes out to be 4 by 5, VS1 over VS2. Now tell me the answer. What is the percentage change in the voltage sensitivity? Can anyone answer? If the ratio comes out to be 4 by 5, what will be the percentage change in the voltage sensitivity? I'm just waiting for something 10-20 seconds. Very good, Cuckoo. Very good. Will it increase or decrease? Very good. Will it increase or decrease? Very good. Now you have learned, I think, Yani and everyone has learned it. Now moving further. Earth's magnetism. You have learned it in your classes as well. So just listen. I will recall one or two things. What are the things that I will recall? If you see a bar magnet, I hope you remember, you can say yes or no. This is a bar magnet. It has two poles, South Pole and North Pole. I hope you know. It has two poles, South Pole and North Pole. One more thing I will tell, the line joining the two poles is called as magnetic axis. These are the simple things. Line joining the two poles is called magnetic axis. The pole strength, now you know that pole strength is positive M and negative M. I hope you know that. This is known as magnetic charge. The pole strength of North Pole is positive M, South Pole is negative M. Now, one more thing that I will say here, be connected. Only after that you can learn something. Now, one more thing that is very simple. It's magnetic moment. What is the direction of magnetic moment of the bar magnet? What is the direction? Is there anyone who remembers this one? You can directly say yes or no if you don't remember. What is the direction of magnetic moment? Very good. Very good, Yani. From south to north. Very good, Kuku. South to north. Now, one more thing I will ask. The next punchline that you should remember all the time is when you, that is very simple line. If you place the bar magnet in some external field, what will happen to it? If you place the bar magnet in some external field, what will happen to it? What will happen? External field will try to align it in its direction. Do you remember this point? Like what I am saying, I can draw a diagram for the same. Like suppose there is a bar magnet like this. This is South Pole, this is North Pole. And it is placed in a uniform magnetic field B, such that. Now, what will happen? This magnetic field will try to align the magnet in its direction. That means this magnet will rotate in the anti-clockwise direction. This is the property that you should remember all the time to proceed further, that magnetic field or external field will always try to align the magnet in its own direction. That means this magnet will try or will rotate anti-clockwise direction. Now the next property is that everybody remembers from class, very basic class 6, 7, 8, that if you suspend, I'm not writing it down, if you suspend a bar magnet freely, and it can rotate in the horizontal plane, then in which direction it will stop, or generally you can say it will stop in the direction of north and south direction. I hope this point is very much clear to you. So what I'm saying, freely suspended bar magnet aligns in the geographic north and south direction. Is this point clear? Now my concern is, if you can combine these 2 points, if you can combine, let's suppose this is point 1, this is point 2, if you combine these 2 points, we get some interesting thing. What is the interesting thing? You know that magnet can be rotated by magnetic field. You know that. From the second point, what you can see, magnets can be rotated by magnetic field. And in the second point, you are seeing that a freely suspended bar magnet is automatically rotated in the north-south direction. So what is the conclusion here? That if I suspend a magnet freely and it is aligning in the north-south direction, that means there must be a magnetic field in this direction. or a component of magnetic field must be in this direction. Only then my magnet is aligning in this direction. Because who can align the magnet? Some field can align the magnet. So what is the source of this magnetic field? What is the source of this magnetic field? The source of this magnetic field is our Earth. That's how we recognize that our Earth behaves as a bar magnet. I hope this point is clear to you. That's how we recognize that our Earth behaves as a bar magnet. Now, our Earth behaves as a bar magnet. So, look at the other slide. Let's suppose this is our Earth. This is our Earth. And for the allocation, you can see this is our North Pole. This is our North Pole. This is our South Pole. These are the geographical North Pole and geographical South Pole. Am I audible to you? Am I audible to you? Okay. Yani, you can ask. You have raised your hand. You can ask. Yani, I am listening to your question. You can type in your question. Okay. Now, the important thing is that our Earth behaves as a bar magnet, and I am giving you one simple homework that what is the phenomena behind the magnetic field of Earth? How Earth is creating a magnetic field? You can read out it in your NCRT books. It is clearly mentioned. Okay, okay, Ani. I am audible. Okay, done. Now, what I was saying, the Earth behaves as a bar magnet. So, where is the South Pole and where is the North Pole of the Earth? So, it was observed that near the geographical north, there is the South Pole of the Earth. And near the South Pole, there is the North Pole of the magnet. Now, this may be a little bit confusing to some of the students. Now, I am repeating my words. Earth has some geographical north and south pole. Everybody knows that. The geographical north, south, east, west. Now, next point I am talking about, Earth behaves as a bar magnet, and this bar magnet has two poles, north and south. So, north is near to the south pole, south is near to the north pole. Very much clear. Now, next point I am saying, the plane perpendicular to the bar magnet, to the Earth magnet, is known as magnetic equator of the Earth. Is known as magnetic equator of the Earth, or you can write it as magnetic equator. Next point. If Earth is a magnet or it is behaving like a bar magnet, it must have some magnetic field lines. So you can see the magnetic field lines of the Earth like this. These are the magnetic field lines of the Earth. What is the point to be focused here? Just try to be a little bit focused here. Can you see that this or these are the points which will which we will call poles or magnetic poles? These are the points that we will call magnetic poles. Clear? In the diagram, you are seeing that this distance is very large, but this is not the largest distance. This is the smallest distance. Uh, can be ignored in some rough calculations. This distance can be ignored. Now, my question is, you can clearly see that at the poles, magnetic field lines are perpendicular to the surface of the Earth. This is the surface of the Earth, and magnetic field lines are perpendicular to it. So, one thing you can remember, field lines are perpendicular to the poles. And the next point, you can see that at this point, you can see these are the locations where diagram may be not that much indicative, but you can sense that at these locations, field lines are parallel. And this is what equator. So what are the two punch lines? At equator, field is parallel to the Earth surface. at poles field is perpendicular to the earth's surface. Can you make these two punchlines out of this discussion? So what are the important things you can conclude after this slide? One is earth has a bar magnet which has a north pole near the geographical south, nothing else. Moving further on the next slide, there are two or three basic definitions that you should remember. What is geographical meridian? So just listen to me, just look at me. The plane, or you can say the vertical plane. Plane is like this. This is a plane. The plane, the vertical plane passing through the geographical axis at a point is known as geographical meridian, or you can see the definition. A vertical plane passing through the geographical axis is called geographical meridian. Clear? Like I am sitting here and I am saying there is a north pole, there is a south pole behind me. So the plane passing through this line is known as geographical meridian. Clear? Simply, what is magnetic meridian? Now listen to me very carefully. If you want to learn something, just listen to this sentence and this will be done. What I'm saying, you have a bar magnet. One thing that you should know, freely suspended bar magnet I'm talking about. You can suspend a bar magnet freely in two ways. Listen to me, two ways you can suspend a bar magnet. One is such that it can move in the horizontal plane only, like this. Can you see the pen? It can move horizontally only. This is the one way. You have hinged it like that, and it can move in horizontal direction, like your compass. Have you seen compass? Like your compass, it can move only in horizontal plane. And another way to suspend it is in the vertical plane. It can move in the vertical plane only, not in the horizontal plane. So these are the two ways you can suspend a magnet freely. Now coming back to the topic. You have a, whenever I say freely suspended bar magnet, you must ask one thing, in which plane it can move. So now I am saying I have a freely suspended bar magnet. So your question is, in which plane? In horizontal plane it can move. Clear? This is freely suspended. Now it will move in the direction of north and south. It will move and align itself in the direction of north and south. Now it is stable in the north south direction. Clear? Now the plane passing through this magnet in this position is known as magnetic meridian. Are you getting my point? You have taken a freely suspended bar magnet. It has aligned itself in the direction of north south direction. When it is stable, the vertical plane passing through it is known as magnetic meridian. You can see the definition on the board. A vertical plane passing through the magnetic axis of a freely suspended bar magnet, which is free to move in the horizontal plane, is called magnetic meridian. I hope this is clear. If you can identify this definition, then it's become very easy for us to move further. What are the components of Earth's magnetic field? What are the components of Earth's magnetic? The meaning of this definition is the quantities which are required to completely locate or completely find the Earth's magnetic field are known as components of Earth's magnetic field. Like suppose, listen to me again. Earth's magnetic field has two things. One is magnitude, one is direction. And to find both magnitude and direction, the quantities that are required are called components of Earth's magnetic field. You can see the definition. The physical quantities required to determine the magnitude and direction of Earth's magnetic field. What are these three components? Angle of declination. Okay. This one now, Yani, you are talking about this slide only. Do you want me to explain it or you want to write down the things? Okay, I'm explaining it again. Can you see this is a bar magnet? Just imagine this is a bar magnet and I have suspended it freely. in the horizontal plane. So it is moving, and suppose it has aligned in this direction, in the north-south direction. This is north, this is south. When it is stable, I have passed a plane through it. Like suppose this is the plane. I have passed a plane through it. So this plane, which is in vertical direction, is known as magnetic meridian. In your books, you might find a different definition. That's a different thing. But what is more important to us is to remember this definition. This is the basic thing that we will need every time. So in your notebooks, in your books, you might have different definitions. So just stick to this one, and this will be beneficial for you. I hope this statement is clear. Vertical plane passing through the magnetic axis. Magnetic axis means magnet, north and south. Freely suspended bar magnet, which is free to move in horizontal plane. Horizontal plane matlab it will align in the north and south direction. It will align in the north-south direction. So this is what magnetic meridian. What are the three components of Earth's magnetic field? One is angle of declination, that we will denote by theta. Another is angle of dip, that is denoted by alpha. And next is horizontal component, which is denoted by B, horizontal. Clear? So in the next class, we will discuss about these components and do some questions of Earth's magnetism, and then we will jump towards the EMI. So try to join it again, and we will discuss in the next class. Till then, bye everyone. Take care. Keep learning.